Hi, my name is Michael Hind. I work for IBM Research as a distinguished research staff member. And today I'd like to talk to you about a topic called trusted AI. IBM Research has over 24 researchers working on this problem of trusted AI, and there's a lot of material that you can look at offline on this website. I'll cover the main topics in the rest of the slides here. When you talk about AI, in particular trusting AI, there are a lot of parties that are very interested in this problem. It's not just scientists or practitioners or enterprises. It's governments, standards bodies, policymakers, sociologists, etc. And at IBM, we are interacting with all of these bodies. This slide shows you a few of the activities that we have going on in terms of working with the EU higher level expert group on AI. I'll talk a little bit more about that later. There's a organization called Partnership on AI, and IBM was one of the founding 5 members. It's now grown to be about 100 members, including industry, including academia, nonprofits, and so on. We are actively engaging with standards bodies like NIST in the United States and IEEE. We're very active in open source, as you'll see in the rest of the talk. And so on. Lots of activities here. And what's important is to understand that this is not just about scientists thinking about trust or machine learning experts thinking about trust, but it's actually takes a multi-stakeholder approach with different backgrounds in public policy, sociology, psychology, and so on. So getting to the core of the talk, what you're hearing about now is AI is being used certainly in a lot more places. It's not just being able to recognize your voice or suggesting what movies to watch or helping you search the internet. It's also being deployed in high-stake application domains. Some examples would be in credit, trying to figure out which loan applicants, for example, are worthy of credit and which aren't. Trying to look at employment. How can we be more efficient and maybe be wiser in deciding on who we hire, who we approve for raises, who we take actions before they leave the company, and so on. Or even admissions to various institutions, such as education. Again, you have a large number of people who are applying, and we're trying to figure out which ones are the best fit for our institution. And then finally, another example is criminal justice, where we have to make decisions on whether or not to let someone out on parole or where to put policing and so on. And the idea here is to be able to scale, to be able to make better decisions, more consistent decisions. But there's a challenge, and that is since these domains are very high stakes, we don't want to get things wrong or want to have things in a biased way. So what IBM started to look at several years ago was this general space of trusted AI. A lot of the industry in machine learning and the scientists have been looking at how can we make the AI system more accurate? Because if it's more accurate, then it's more correct, and that's what people want. But it turns out there's other dimensions besides accuracy that are important to people. And this slide, which is also the organization for the rest of the talk, talks about these 4 pillars. So the first one is on fairness or bias. We want to make sure that an AI system is not biased towards one kind of group or another. The next pillar is explainability. If an AI system makes a recommendation, we'd like to understand why. What were the important features? Why did I deny that loan? Was there particular aspects or answers on the application that were important to me, important to the system? The next pillar is adversarial robustness. And what this means is it's kind of like security meets AI. In other words, can a bad person sort of come in and understand your model and kind of trick your model? Understand where the boundary points are, and then therefore have applications, let's say loan applications, that are similar to those boundary points, and therefore trick it, or maybe even steal the training data. And the last pillar is related to transparency and governance, which are very much related to each other. And it's looking at the bigger picture. It's saying that when I produce an AI system, how can I understand how the general system works in a big picture? And how can I govern the building of the AI system? All of these pillars need to be supported in a life cycle. AI has a natural life cycle, just like software has a life cycle, and it's how it's constructed, how it's tested, and how it's deployed. And all of these pillars need to integrate with that life cycle. I'll talk more about that at the end. So what IBM research was doing was looking at these topics, and they're very challenging topics. Again, it's not just a question of scientists figuring out, how to measure this and then we're done. It really takes the scientists to be able to do that, but also having people like sociologists and public policy people to come together and to tell us what's the appropriate way to govern AI systems. I'll talk more about that in a second. But what we saw here was there was a big gap between scientists trying to address these problems and also what society needed. You'll see shortly that there's a lot of press, a lot being written about these topics, and a lot of scientists trying to solve these problems, but they weren't necessarily speaking the same language. So what we tried to do to help accelerate this collaboration was to release open source toolkits. So the first one we released back in 2018 was Adversary Robustness 360. The idea here is to have an open source toolkit that allows the practitioners and social scientists to play with these ideas that are coming from science to help bridge that gap and to give feedback to the scientists on whether or not their solutions are actually solving real problems. We continued with this pattern with AI Fairness 360 later that year with a similar idea. Then, of course, in 2019, we released AI Explainability 360 to tackle that problem. And then finally, earlier this year, we released AI Fact Sheets 360, which is a website that talks about the ideas of transparency and governance. I'll talk about all of these in the rest of the talk. The impact for these toolkits has been significant so far, even though it's still early. There was a strong desire from a lot of companies to have these toolkits be under open governance, and IBM donated these toolkits to the Linux Foundation, and they are now, IBM is still very active with these toolkits, but it's now being governed in an open governance way. IBM also included this in our Cloud Pak for Data hybrid cloud offering, so you can get these packages more directly if you're using IBM Cloud. So now I'll focus on the first topic, which is bias. So there are many, many examples in the popular press where an AI system was created to do something that seems reasonable, but unfortunately some bad things happened. Here's just 9 examples over the course of a few years that show some of the ideas here. I'm not going to go through all the details here, but I'll just summarize them. They're pretty much similar in that somebody had a good idea for an AI system, and it worked pretty well on the test data they looked at. But then when it got deployed, somebody else found an issue. And then usually at the bottom there's these blue lines that say, a company spokesman says, "I apologize. We did not intend for this to happen. We're very sorry, and we'll try not to do it again." One example that was in the news more recently was a situation where a company had a credit card they were offering, and there was a husband and wife in the US who had very, very similar credit rating in terms of having a lot of joint accounts and so on. And one applied for the card, and they both applied for the card, and the man got something like 10 to 15 times more credit limit than the woman did, more credit limit. And this was very strange. It seemed that the only difference between the two of them was the fact that one was male and one was female, which raises a lot of issues, certainly. And it's definitely not good publicity, for those companies. So the question is, what can we do when we're building an AI system? How can we try to understand and maybe even mitigate this issue? So one of the things we did at IBM was to create the AI Fairness 360 package, which is an open source package written in Python. The idea here is that we'd like to be able to measure situations, discover situations where there is some level of bias, and then also to potentially mitigate that bias. So what this package does is it has 70 different ways of measuring bias or fairness. And the reason why is not because the world needs 70 different ways. It's because this is where the science is right now. And this is not just machine learning. This is also, sociology. The question of what is fair, there's actually different ways of measuring fairness. And so what we've done is we put them into this toolkit, these 70 different ways. But which metric makes the most sense for a given situation really is going to depend on what the goals are for the stakeholders in that situation. On the right here in the screen, you can see this is a demo we have on the website, and you can see there's 4 different things being measured there, 4 different ways of being measured that are well known in the community for a specific data set and model. The scientists in this space have also come up with ways of mitigating bias. And so the idea is you would measure, let's say you measure a model and you see there's some bias towards men over women. And then the question is, what can we do to try to mitigate that bias? Now, one option would be to go and have humans go and study the problem more carefully. Go look at the training data set and see, is there a bias there? Are we telling the AI system that, hey, men generally should be approved more often because that's what's in the training system? Then that would be a problem with the training data set, and we should go and fix that. However, there's also been some research to say, is there some kind of algorithm that can automatically try to mitigate bias? In other words, if it's looking at a data set and it sees that men are more likely to be approved than women in the training data set, maybe it can compensate for that fact as it builds a model. And that's what these mitigation algorithms do. On one hand, it's attractive to have a system automatically mitigate bias, but given the stakes that we're talking about here, it really makes sense to have a human involved, either doing the investigation themselves, or if they do use a mitigator, to actually go and understand what's happening there, because there's some trade-offs. And maybe your accuracy is not as good, even though you're more fair. And so you want to make sure you understand and are comfortable with that, given your high-stake problem you're trying to solve. So also in the toolkit, we took a lot of effort and time to not just be giving these metrics and giving these mitigation algorithms, but also to do a lot of education. We understood it's not just going to be people who are familiar with Python who are going to go and start hacking and using the code, but we also wanted to make sure that people who maybe aren't data scientists can benefit from the website. So what we did is we put a lot of effort into looking at into creating tutorials, and also the demo, which you saw previously on the right-hand side there, to help people understand the space. And so, like, important takeaways from the website is that yes, there is a toolkit that can measure bias, but there's some very important decisions that need to be made by important stakeholders, such as which of the metrics should I use? Given once I choose a metric, what is an acceptable value? A lot of the metrics go from -1 to 1, where 0 is fair and 1 is very biased for one group, -1 is biased for another group. If I have a value of, say, 0.0001, which is very close to 0, is that good enough for being fair? Or am I in such a situation where maybe that's not acceptable to me? And so figuring out what the threshold should be for acceptable bias is very important, and is not to be something decided by a data scientist, but someone who's looking at overall risk for the company, who's aware of regulations, and so on. And so our hope here is by creating a lot of education in this space, that those people that aren't technically savvy can also communicate and understand what the issues are. And then we also have examples in terms of tutorials and notebooks to show people how to use the system. So the next topic I'm going to talk about is explainability. And this is basically saying that a lot of machine learning systems are learning patterns. They're looking at data, they're looking at decisions. Think of it as loan decisions, right? So here's maybe 100 or 500 loan applicants, and what a person decided should be accepted, approved, or denied. And then we feed this to this magic black box, the AI system, and out comes a model that's going to be used to look at new applicants. And the problem, and that's working pretty well in certain domains. And the question here is, what happens if someone is denied? What can we tell that person? Why were you denied? And since this is not being done by a human, we don't necessarily have visibility into the model of how it's making its decisions. So explainability is a topic of how can we explain things in a scenario like I just said, where a loan applicant was denied and they want to know why, because this is going to impact their life in a substantial way. So this slide talks about some examples where the popular press is writing about this problem, saying that AI is good, but what about explainability? And at the bottom of the slide, we see two examples of organizations who had a better algorithm, a better AI algorithm that was more accurate, but they could not deploy it because the algorithm was not understandable. You couldn't explain how it worked. So maybe before they were using a simple, what's called a decision tree, which could be, hey, if the salary is greater than this and the outstanding debt is less than that, then approve. And that's easy to understand. And then they try to do something more complicated, like a neural net, which is much harder to explain. Then that's a problem. And so this problem of explainability is an important one for enterprises, because a lot of the techniques they're looking at are not explainable, and in some cases can't be deployed because of that fact. So it's not only enterprises that are struggling with this question. We also see examples of regulation that are requiring some form of explanation. On the top part is a snippet of a slide from one of the creators of GDPR, Paul Nemitz. He visited IBM 2 years ago. He gave a talk on GDPR. And GDPR mostly talks about data protection and privacy, but there is a section that talks about the right to an explanation. And what this is basically saying is that if somebody uses a model, an AI system, to make a decision, then the user has a right to get meaningful information about the logic that was used, which is another way of saying an explanation that's meaningful. On the right side of this screen is talking about a law that was passed in the United States in the state of Illinois, and in particular the city of Chicago. And it was concerned about video interviews. So the idea here is you're doing an interview, you're doing it by video, you're recording that. And in some cases, people use an AI system to evaluate whether or not that applicant is a good applicant based on analyzing the video. And so you can see how this could be attractive. If this is good and accurate, it could be help you interview a lot more people, because you don't have to have a human interview and understand and discuss. But of course, it could be dangerous if it's wrong, or even worse, if it's biased. So there was a law passed, and it says a number of things. One of them is you need to tell the applicant that this is happening. But the part that's relevant for this presentation is the law says the system needs to be able to explain itself. So again, another example of regulation that has the reasonable idea of, if you're going to use an AI system to do something that's very high stakes, then it should be able to explain itself, which sounds good. Except, what does that really mean, right? So, right now I'm trying to explain something to you, and you'll be the judge on whether or not I'm succeeding. Just by the fact that I'm trying doesn't really mean I'm succeeding. This slide talks about what an explanation can mean to different people. So in the middle, we have this black box, which is this AI system. And then we have different kinds of people, different personas. So on the left over here, we have a data scientist, and she wants an explanation because she wants to understand if the system is working well or not, and if not, how can she improve it. She wants to sort of debug the system or gain insights into how to make it better. She's very technical. She understands AI, and so she can deal with the deep technical information coming back in the form of an explanation. The next persona with the laptop is a developer, also technical, but in a different way. The developer doesn't understand data science or AI. They write regular old-fashioned code, and they want an explanation that's going to tell them how the system works as they integrate their regular code with it. But they can't probably handle an explanation that's very detailed in AI technical terms. At the top, we have a physician. She happens to be a dermatologist, and she's going to be using the AI system to diagnose if a lesion is cancerous or not. She's very technical in her domain, in medicine, but she doesn't know AI. So an explanation for her could be using medical terms, which would be very appropriate, but not AI technical terms. The next person is a regulator. This person wants to understand how the system is working in general and wants to make sure that it's fair. So they would like an explanation of how the system works in general. What's the general way it works, and to be able to assess whether fairness is there. And then finally, the last person is my dad. My dad's not a computer scientist, not a machine learning expert, not a physician. He has this lesion on his hand, and he went to the doctor, and he wants to know, is this something I should worry about or not? He doesn't understand medical terms, and so the explanation he gets of whether or not it's cancerous needs to be something that he can understand. And so what I'm trying to illustrate here is that that box in the middle, who we've just required to give an explanation, has a very, very hard problem. It needs to know who is actually asking the question, who am I explaining this to, and what are the right ways, appropriate ways to explain to that person. And this is not something you're yet seeing in legislation. So we actually saw a big opportunity to be able to have the scientists communicate this challenge to the policymakers, and get an ongoing collaboration to be able to understand each other and come up with hopefully good regulation. To aid us with this, we created another toolbox, AI Explainability 360. And what it has is a bunch of different algorithms that explain things in different ways, right? So one algorithm, for example, will say, if I have a loan application, and it was denied, I can tell you which of the questions that you answered were most important, such as your salary, the number of loans you defaulted on in the past, maybe how often you've moved around, number of outstanding credit cards. I can tell you which of those features are the most important. That's one way of doing it. Another way of doing it would be to say, well, you've trained me on a bunch of other applicants, and this new person, let's say Joe, who I'm trying to assess, looks a lot like these three other applicants, which you told me should be denied. And so I'm telling you, you should deny Joe because Joe looks a lot like these three others, right? That would be something more appropriate for maybe a loan officer to be able to understand why we're actually denying poor old Joe. So if you go to the website, you'll see a demo, and it will show you these examples in more detail. What's in this toolkit is a bunch of algorithms. It's actually 10 algorithms, 8 algorithms initially from IBM research for doing explanations. And we just added two other algorithms from the scientific community. So there's now 10 algorithms. As I mentioned, there's this demo that deals with the credit scoring situation and gives examples. We gave a lot of examples here. So here we've got 13 tutorials that are created as Python notebooks, covering a whole bunch of different use cases. And you can see how explanations are being used. Quite often with software, it's really important to have examples because then you can, if you want to apply it to your particular case, you can see quite often that it matches some other use case or it's similar, and then you can sort of copy and paste and modify. So that's valuable. Um, and we've also written a paper on this, and I'll just show you one aspect of this on this next chart. I don't expect you to understand all of this, but I wanted to try to illustrate some of the breadth and depth of this space. So the title of the paper, kind of summarized what I've been saying. One explanation does not fit all. We saw in the previous slide there were all these different kinds of people that all needed different kinds of explanations. What this is showing here is basically a decision tree on which of the algorithms in the toolkit might be appropriate, right? So for example, and it also illustrates places where researchers can do further research. So right now, one question is, when you ask for an explanation, do you get it all in one shot, or do you have an interactive conversation, right? So you may say, why was I denied a loan? Maybe you get a paragraph or a bar chart or something that comes back to you. That would be one shot. Interactive would allow you to drill down and say, okay, you said my salary wasn't sufficient. What would be sufficient? Or can you tell me where you found my salary? How did you know that? Or is the source reliable? Something like that where you drill down. So far, all of the work that we're aware of is all in this sort of static branch, meaning that the explanation is given as one shot. Here it is. Here's a paragraph or a chart or a graph, whatever it may be. Interactive is a very, very appealing, but right now there's not much going on in that space. Then when you look at static, you might say, well, am I going to try to understand the data, the training data, or the model? A lot of work is looking at the model, interested in the model. That's the examples I've been giving. And then when you look at a model, there's a question of, are you looking at what's called local or global? Local means a specific instance. Why was my dad diagnosed with skin cancer? Versus how does the overall system work for everyone? And that's what global means. Finally, if you're looking at, let's say, local, then there's a question of how do you construct the explanation? Many systems in this space constructed after the fact. So what happens, it's kind of like saying, I made a decision to go buy, let's say, pizza, and then someone asks me, why did you decide on buying pizza? And then I tell them based on what I think the answer, what the answer is. That's sort of post hoc. I'm coming up with the explanation after the fact. Self-explaining kind of says, well, as I'm making those decisions, I'm writing down why I'm doing things. And so there are techniques in that space, but most of them are in the post hoc space. And then finally, when you get down over here, which is where a lot of the work is, it's a question of how are you actually explaining? Are you explaining by the features? Features are answers to the loan application. That's what I gave an example before. Samples would be, show me other people that are similar to this person. So those are the two examples I gave. Most of the work in this field is down right here in this leaf. If you ask about someone, if you've heard of the term Lyme or SHAP, they're all down in this space here. And the point of this slide was to illustrate that there's many, many different techniques you can have for explaining things that may be appropriate in different circumstances. And this toolkit is very broad in that sense, and that it has a lot of these examples. And I'm sure there'll be new algorithms, new ways of doing this as we go forward in the next few years. The third pillar of trusted AI is what we call adversarial robustness. So the problem here is one where you may have, let's say, the bad people trying to attack your AI system in various ways. And as with the other two topics, there's been a lot of press that talk about this. So here's an example of the kind of things that can happen. The first chart is showing an AI system that was trained to recognize signs, traffic signs. And one in particular, it was able to recognize the sign on the left, the stop sign, but it was also able to be fooled. So the system that was very accurately finding the stop sign, if you put, let's say, that yellow Post-it note in that spot right there, then the system would get tricked and it would think it was a speed limit sign, which to us is just mind-boggling. It doesn't look at all like a speed limit sign, but it illustrates how these AI systems are learning, quote unquote, learning in a different way than we do, right? Which has its strengths and weaknesses. And here's an illustration of weaknesses. This example can be done in different modalities. This one is image. There's also one for voice, where you can have a person who's speaking and you add a little bit of noise, and we would understand it as the same person, but then the system would recognize it as something completely different, different words than what we actually hear. In the middle is an example of stealing the training data, right? So remember, the training data typically is something that companies keep close to them. It's how they train their system. And it's hard to get good training data sets. So they want to keep it, close and to themselves. So here's an example where by a bad person asking questions of the model, they were able to reconstruct a training data image. So the one on the left is the real image in the training data that the company did not want to release. And then people who were trying to understand things about the model were probing the model and were able to understand get the picture on the right. And to us, that's pretty darn close. So it's possible to actually steal the training data without getting access to it, but just by probing the model. And then finally, the last example is an example where you have a person, man over there, who wore these funny glasses. And by wearing those funny glasses, the system totally recognized him as someone else, who was the famous person on the right. So these are examples of how AI systems can be fooled or have their training data stolen by adversaries. And so to help address this problem, what we've done in IBM research is create a toolkit called IBM Robustness 360. And what it has is ways of attacking AI models that are known and have been published. You can see on the right there is a whole bunch of bullets, and after them, there are names. Those are all publications published in the literature in the space. And so there are known ways of attacking systems and then known ways of preventing attacks. And they're both in this toolkit. The idea, of course, is to focus on the ways of preventing attacks and encourage people to come up with new algorithms and add them to the toolkit. Finally, the last topic I want to talk about is governance and transparency. So this is looking at a bigger picture, and it's basically saying lots of people care about transparency, which is how does a system work in general, right? And this is not about an explanation per se of why was I denied a loan, but tell me about the bigger picture of an AI system. How was it built? That's what transparency is about. And then governance, which is, are there ways to be able to track how it's built and to control how it's built in a way that satisfies whatever the needs are of an organization. So in both cases, we have a technology called fact sheets. I'll talk more about that in a second. And it's appropriate in both these situations. So going on the left, the idea here is I have a consumer. In this particular case, it's at a vegetable stand, and they want to buy, various things, and they want to know something about them, right? So, often we say, what country they came from. We may say whether they're organic or not. Maybe there's an expiration date. It's some level of information about the product so that a consumer can make an informed decision. And that's what transparency is. So for AI, the question was, well, what would it be? What would make sense over here? People are very concerned. You have a model that, let's go back to loan application, a model that is approving loans, and people are really worried that maybe there's some kind of bias in the system, or maybe there's a bug and people don't understand it because they can't explain it, or maybe it's attacked and hacked by a bad person. So how can we get some level of transparency to be able to explain it to the consumers and so they have trust in the system? So we were looking at this problem for AI, and before we got very deep, we decided to say, well, wait a minute, the general problem of transparency is not unique to AI. There's many situations where people want to trust a product, what do they do? So on the right, you will see some examples. The first example is a nutritional label, which is familiar to many people. This was a way that consumers of packaged foods could understand a little bit about what was in the food. It didn't tell you exactly how it was built, but it did tell you information that hopefully you found appropriate, such as the calorie intake, the level of sodium, vitamins, and so on. It turns out it took about 20 years for the idea of having a label to finally getting a standardized label to happen, right? So it took 20 years, at least in the US, for that to happen. Other examples in blue there is something also in the US called an Energy Star label. This is used for appliances, and it's trying to answer the question of, I want to buy an appliance. I know they use a lot of electricity. Can you tell me if this one is energy efficient or not? Now, clearly, there's a wide range of energy efficient. Some could be more than others. Some could be, great, or maybe good, or maybe fair, or poor, and so on. But when the makers of this label came about, they decided to make it very, very simple on the consumer. The consumer probably doesn't want all that detail, and they decided to make it simple, to have it be basically one bit. It is efficient or it's not. So they pick a threshold, and when it's above that threshold, it is efficient. You get the label. Another similar example is in the lower left there, the 0 to 3. That's used for children's toys. And people want to know, is this particular toy appropriate for children under the age of 3? And when you see that sign, that means it's not appropriate because there could be some issue probably related to choking. And then finally, the table that you probably can't see, that's for bond ratings. Another example where you have consumers who are trying to buy bonds, but they're not experts, financial experts. So they're trying to get a feel for the level of risk. And what we have is rating agencies who decide whether or not a bond is high risk or low risk, giving them letter grades. So that was just some of the examples that motivated us to say, okay, do these ideas apply for AI? What would it look like for AI? And we quickly learned that it's not going to be one bit of information. It's not going to be, I can trust this system or not, at least not right now. And so we wrote a paper 2 years ago about this called Fact Sheets, and gave some suggestions on possible questions that could be answered about the system. And some of these you've seen already. They deal with bias or explainability or adversarial robustness. But some of them are new. Some of them could be, what's the intended use of this model, right? So that's a very important thing, because quite often in AI systems, you reuse models. And I'll give you a concrete example. Let's say I work for a bank and I created a model to be deployed in a very rural place, right? Let's say the middle of the United States in North Dakota, okay? And it's looking for credit applicants. It's trying to evaluate them on whether or not they should be given credit. And some of the things it looks at is, of course, their salary, but also, do they own a home? Do they own a car? And so on. And let's say the model works really well, and I'm really happy with it. And now I have a colleague down the hall who wants to create a similar model, but now it's for an urban area, let's say New York. And he comes to me and he says, Mike, I heard your model is doing really well. I want to apply it to New York. Can I go in and do that? And the answer may be yes, it should work well, or maybe no. Because some of those questions, like, do you own a home or do you own a car, are going to get very different answers in an urban area where most people don't own cars or homes. And it doesn't mean they're not good credit risks. It just means that's just the way it works in that particular location. And so this illustrates why it's important to be precise on what an algorithm is intended use is. In this particular case, my initial algorithm, my model, was intended to be used in rural areas, and it works very well for that. It may work well other places, or it may not. And so that's why an important fact that we put on these fact sheets would be, what is the intended use? So that someone who's going to reuse it, if they see they're using it for a different use, they should be aware that there could be some issues here and make sure they test it more thoroughly. what we've recently done this year is we put out a website that we call AI Fact Sheets 360 that goes into a lot of these details. It gives examples of fact sheets, um, and also talks about a very important problem, which is how do I know what I want to collect, right? So if you follow the analogy to nutritional labels, you might think, well, okay, I get this. Someone's going to decide what the magic questions are, and then I'll just answer those questions and I'll be done. And you could do that, and some people in the community are suggesting that, but we feel strongly that that can be very dangerous because the information that is needed is going to depend a lot on the use case and the industry that you're working in. So, for example, in a regulated industry that has a significant concern about bias, there'll probably be a lot of information, a lot of details that you will want in that scenario. And maybe you won't necessarily need it in other scenarios that's not dealing with, say, humans. So we feel that the fact sheets should be tailored to a particular use case. And on the website, we have a section we call methodology that walks through a 7-step process for how to get useful fact sheets for a particular use case. And you can see the 7 steps on the top right of this slide. The website also talks about governance, and I'll talk about that in subsequent slides in a second. And as I said, gives lots of examples, also links to papers and videos. There's over 24 hours of videos on various platforms that cover this area and related areas like bias, explainability, robustness, and so on. And you. Okay, so on this slide, we have AI governance, and there's 3 important aspects of AI governance. We've spoken to several dozen customers about this, and we've seen these 3 needs that come up. The first need, which is a very, very pressing need, is the need to automate the documentation of what's called the AI lifecycle. The AI lifecycle is the construction and deployment of an AI system. And there's a strong need to document that because various people within the life cycle need the information. I'll show you that in a second. But also regulators, for example, need that level of documentation. So documentation, I'm talking about a fact sheet here. The second need that we hear is the ability to specify and enforce policies that are actionable. So what I mean by this is you may have a policy in your organization that says, my system should not be biased. That's a great policy, right? A good goal we'll probably all agree to, but it's not very actionable because, well, what does it mean? How do I know if I've achieved that? We already said a bias, there's many different ways of measuring bias, and what is acceptable and what is not is another important aspect of that. So you need to have a much more concrete and precise rule that says, hey, I will measure bias using, let's say, disparate impact, and it will be acceptable if the value is less than 20% or something like that. So that the second part for governance is specifying these rules that are actionable and enforcing these rules during the process of constructing the AI system. So that when the data scientist creates a model and they measure accuracy, they may also measure bias, and they will check to see if it's appropriate or not. And then finally, the third bullet is looking at how we can get the various stakeholders of the life cycle to collaborate with each other, to share information so that they can be more informed and have better conversations and collaborations going forward. I will now illustrate that with an example. So this slide gives an example of the AI lifecycle. On the left, we have, in this particular case, 4 different personas. The first one is the business owner who starts out the process. They've requested an AI model gets built to solve some business problem. This could be help, do credit scoring on loan applications. The next person is a data scientist. They're the ones who will take the specification and requirements from the business owner and decide whether or not, and build a model for that. The next person is a model validator. This is a role that's sort of like a testing role or a quality assurance role. And that's going to take the model from the data scientist, but before it actually gets deployed, make sure that the level of risk is not too high. So do some kind of testing, do what's often called creating a challenge model, which is a simpler model to see if the sophistication of the data scientist model is actually needed. And then finally, if all goes well, the model gets deployed, it goes into operations, and you have an engineer who's monitoring the model to make sure that it performs well. Each of these personas have information about the life cycle. The business owner knows why the model was being built. They know the level of risk. Is it high risk, low risk, medium risk of it, and the intended use. Finally, then the data scientist has similar information in terms of the data set, the accuracy, the bias information, and so on. The model validator is the one doing the testing, and the information from testing will also be useful. And when the model is deployed, the operations engineer will want to know about how it performed. So our vision is all these facts should be collected into a central place, and then you can query this central place to be able to understand and get reports about how the model was constructed. So now all these personas in the life cycle can come and compare and understand, but also people outside, like a chief risk officer or a regulator, can come in and understand what happened during the construction of this model. This information is available on our website. It is a link to a smart paper that we've written about this. It's basically a white paper. And also there was a blog and a webinar with an analyst that's discussing this topic. So my last slide is just to summarize the 4 pillars of trustworthy AI, as I mentioned, are fairness, explainability, adversarial robustness, and transparency. At IBM Research, we've created toolkits for these spaces with lots of technology and are very popular. So I encourage you to go visit those websites, and each of them has a Slack channel. So if you want to interact with us and the community in general, you can ask questions or contribute to the open source toolkits. Thank you for your time, and I hope you have a good day.